Okay, so on the top, we have the multiplication here. On the bottom, we're going to have common denominator of sine squared x times cosine squared x. And on the top of that, it'll be sine squared x plus cosine squared x. And what is the top of that? What is that equal to, I guess I could say? 1. So this is 1 over cosine squared x sine x over 1 over sine squared x cosine squared x. What would my step now be?
I saw a plus in between the bottom part of, like the very bottom thing, somehow. And I was thinking, wouldn't that just be 1? But no.
Turn the x over.
Well, I guess I also turned the x over and still had the original x.
What's my step now? We got a fraction over a fraction. Keep, change, flip. I don't know who came up with that phrasing initially, but I'm glad they did, because it makes doing these problems so much easier to explain what's happening. Take the bottom fraction and turn it over. Like, keep, change, flip just makes sense. My mom used to do keep it, change it, turn it. So I did that for a long time, and then people would come through my class saying keep, change, flip, and I was like, that's so much faster to say.
I remember like some of the things she would tell us like that, like gore and land. I still think about them. Or no, gore.
Yeah. I know, that's what we had. Be the pretzel for cross multiplication, be the rainbow for distributive, all kinds of things like that. What am I left with? Sine x. Scary problem turned out not so scary, which is always good. Let's see, that was 32, right? Yeah. Okay. Combine the fractions and simplify to a multiple of a power of a basic trig function. So, like, for example, 3 tangent squared of x. So that's what that means. And that doesn't mean that they won't simplify, like, that they're all only going to simplify to that. Like, they could be, more simple than that. But as long as it's at least in that form, it's fine. 34. 1 over 1 minus sine of x plus 1 over 1 plus sine of x. How would I have to go about solving this?
Is this the thing where you multiply it by like the 1 minus? Okay, this is what I was trying to figure out the other
Conjugate?
day.
Is that what you're trying to
That's
say?
what it is.
Yes, so I'm going to multiply them by the conjugate because I need to get a common denominator, right? So the one on the left is going to be 1 plus sine x, top and bottom. The one on the right is going to be 1 minus sine x, top and bottom, which will give me the common denominator. Now, in this case, it is the conjugate. If the bottom was not 1 minus sine of x and 1 plus sine of x, like if, say, the one on the right was 1 plus cosine of x instead, we would be multiplying this by 1 plus cosine of x. So we don't have to use the conjugate in this sense, but we do because the denominators are conjugates of each other. But yes, there was a problem we did the other day that we needed conjugates for. I don't remember which one it was now. But anyways, but yes, that's is what we would need to do. I'm trying to write on the crack of the iPad and it's not working.
I just made a new one.
Yeah, it's like I could do that too. All right, so on the bottom, would say go ahead and multiply this stuff through. Sometimes it's better to not, just knowing what the end goal is. In this case, I would multiply it through and just go ahead and get that. So it's going to be 1, and these are difference of squares, so it'll be 1 minus sine squared of x. And knowing that, like, with this, like, knowing that something's going to end up being squared, I know that I can think Pythagorean and see if that's going to work. And obviously, in this case it will, but in all of them it, won't necessarily be the case. Oh, no. Oh. I thought it was gone. I was like, no! Okay. 1 plus sine x plus 1 minus sine x.
I was wondering what that line was for, and then that's when I realized it's
the top of the fraction.
Wrote the bottom there.
So sine of x's are going to cancel on the top. The 1 minus sine squared of x is going to be cosine squared of x. So this is going to be 2 over cosine squared of x. Now, how else, ignore the 2 on the top, how could I rewrite 1 over cosine squared of x? Oh, the heat probably. Changing that is probably what it is. The heat really kicked on. It was cold earlier, and then I flipped the heat, and now it's like getting toasty.
Yeah, it feels good. It was cold in this Greer's room.
That's a rare thing for their classrooms.
I think it's because she had to open the window because it was hot in there.
Oh, yeah, probably. Especially if you sit on that side of the room. What'd you say this is?
The draft.
Secant squared.
Yeah, so this is going to become 2 secant squared of x. And that's the form that they were saying that they need to be written in.
We love secant.
Let's see. 38. Sine of x over 1 minus cosine of x plus 1 minus cosine of x over sine of x.
I'm gonna make sure I have plenty of space to write if you need to multiply stuff.
So what am I going to have to... Oh, now I can smell the heat. What am I going to have to do with this one now?
I don't know yet, but I don't like it because we have to add them. Why can't we multiply them?
Yeah, multiplying would be much nicer.
It could just be 1, right? To multiply it.
Yeah. So I have 2 fractions and I need to add them together. So what is always my first step? Okay. So I need to multiply the one on the left by sine of x over sine of x, one on the right by 1 minus cosine over 1 minus cosine. So this is where I was saying, like, the temptation would be to do the conjugate. even in my brain, like on the last problem, I was like, oh yeah, to multiply by the conjugate. And then I was like, wait, I'm trying to get a common denominator, so that's not always the case. So this one would be sine of x over sine of x. This one, 1 minus cosine x over 1 minus cosine x. So the denominator, this is one that we may end up needing to leave it separate, but I'll go ahead and multiply it through and we'll just see what happens. Actually, let's leave it separate and multiply it later if we need it. Because it's a lot easier to go and multiply it than it is to like undo it. So let's just leave it separate for now. Alright, so I've got sine squared of x. Then I'm going to have 1 or plus 1 minus 2 cosine x plus cosine squared of x. Does that sound right?
Yeah, I think so.
Okay.
Sounds reasonable.
So now on the top, what do I have? Yes. I was like, wait a minute, I need to register because I was waiting for the signs, like the 1 plus 1 minus. So I was like, wait a minute. No, it just needs to be 2. So 2 minus 2 cosine x over sine of x times 1 minus cosine of x. Ideas now. My goal is to try to cancel something.
Oh, okay, so we have the 1 minus cosine of x on the bottom, but on the top we have 2 minus 2 cosine of x. So we have like basically double on the top of that on the bottom, except it's a sine of x on the bottom. But can we like get rid of those and then it's just
How about I
cosecant?
factor out a 2 first?
That's really smart.
So I would be left with 1 minus cosine of x over sine of x times 1 minus cosine of x. So those things are getting canceled. So I'm left with 2 over sine of x, which is 2 cosecant of x. Let's see. Fun stuff here. All right. Write each expression in factored form as an algebraic expression of a single trig function. So we have 1 minus 2 sine x plus sine squared of x. And I want to factor this. Perhaps it would help if I rewrite it like this.
Yeah.
Sine squared of x, I'm like dying, minus 2 sine of x plus 1. What does that now look like?
One of those triple thingies.
Hmm?
It just looks like a, what's it called?
You know, like the
Perfect
square trinomial.
Yeah.
Yes.
That's what I was
Okay.
trying to say.
Looks like a polynomial, okay, quadratic equation. Except for now I have trig functions. Now, you probably visually don't see how to factor this right now. Okay? Maybe you do, maybe you don't. Okay, so I'm going to show you something we call U substitution, which I may have shown you briefly last year. And I was like, you don't really need to worry about this yet. Like, I'm just like showing it to you. But it'll make your life a little easier. So we say let U equal sine of x. And that's critical to remember at the end. Okay, so this is called U substitution for Riley. She's not thoroughly confused on where U came from. So anywhere that I see anywhere I see sine of x, I'm going to replace it with U. So sine squared of x is going to be U squared. Minus 2U plus 1. U substitution ends up being a pretty big thing in calculus that we end up using a lot to rewrite things that we don't know how to deal with. So that's why I like to show you. So now you probably can factor this. Now you might have been able to before, but let's hypothetically say you couldn't. This was the only way you knew how to do it. What would this factor into? Because this
U minus 1
is a special type. Yep, U minus 1 squared, okay, because it is a perfect square trinomial. So now at this point, we have to replace back. And so this would be sine of x minus 1 squared would be the original in factored form. So if you need to use u substitution, that's fine. If you're like, nah, I've got this under control, I knew sine of x is literally just like x squared and whatever, and I just totally fine. Not a problem at all. Let's see.
I do remember the u substitution, but I also remember that it was really confusing and I didn't really understand it.
It's just rewriting things in terms of something else that you know how to use to make it look different. Because I've had a lot of students who just cannot process that like sine squared minus 2 sine of x plus 1 is just like x squared minus 2x plus 1. And like that's fine. Like it's like the first time I tried to get it, it was like, what? Like I didn't understand, but like rewriting it helps you to see it a little better. So write each expression as an algebraic expression of a single trig function. So for example, 2 sine of x plus 3. So 48 tangent squared. They use alpha. I'm going to use theta because I don't feel like drawing a fish. Minus 1 over 1 plus tangent of fish. Theta. So I need to simplify this. In my previous class, they tried to tell me I could cancel tangent squared and tangent, and I was like, no.
I mean,
We weren't doing exactly this, but something like this, they tried to do that, and I was like, no. Perhaps if I gave you something like x squared minus 1 over 1 plus x, what would you do? You can even disregard the bottom for right now. What would you do to the top? Okay, because it's a what? What special type is that?
I know what it is. I forgot what it's called. Virginia, go.
I know that
It's not perfect square trinomial. It's the other one.
Difference of
Difference of
squares.
Difference of squares, okay? So this would factor into tangent of theta plus 1 times tangent of theta minus 1. Because this term is being squared and 1 is being squared. So that's why I can do it that way. Over 1 plus tangent of theta. Now what happens? Yep, those cancel even though they're in different order. So I'm left with tangent of theta minus 1. You got it under control over there.
Yeah, I'm just thinking fish.
Tangent of fish. Fishy, fishy. Alright, 50. Tangent squared of x over secant of x plus 1. How about this one?
I don't like that one.
When you see a squared term, if something doesn't immediately cancel, what should you be thinking about?
I do like the one that looks family. Secant squared minus 1 on the top.
Okay, so a Pythagorean identity, so tangent squared would be equal to secant squared minus 1.
Okay, I'm not so scared of that plus 1 anymore.
Now, what do we have on top?
Secant x minus 1, secant x plus 1.
Secant x minus 1 times secant of x plus 1. So difference of squares again. And we cancel and get secant of x minus 1. Now, in your notes, did I have the thing about the square root of a trig function? It's like one sentence, so I don't know if I put it in there or not. If it was, it would have been right at the end. Okay. So, square roots of trig functions must be positive so they need to be written in absolute value bars. Now, that doesn't mean I'm writing the square root in an absolute value. It means my final answer is written in absolute value bar so that it's positive. So, with 70, I have the square root of x squared plus 1, but they say that x is equal to tangent of theta. Now, why they don't just go ahead and write it for you, I don't know. But the square root of the tangent squared of theta plus 1 can be written as what?
Secant squared.
Yep, so the square root of secant squared of theta. Now, the square root of secant squared would be what? Secant of theta. And this is where the absolute value bars come in, is they get put like that. Which just says that when I'm all done, it has to be positive. Now notice, this is when there's a 1 here, okay? If there's a different number, then I've got to basically factor that number out first. So if it's something like 72, the square root of 36 minus x squared, and they tell me that x is equal to 6 sine of theta. That means the way this gets written would be the square root of 36 minus, and then in parentheses, 6 sine of theta squared. Now, I'm going to be obnoxious and write out every step. You wouldn't have to write out all of these steps. Would be the square root of 36 minus 36 sine squared of theta. Since there's a 36 in both pieces, I can factor it out. So the square root of 36 times 1 minus sine squared theta. What's 1 minus sine squared of theta?
Cosine squared theta.
Yep, so 36 cosine squared theta. Now I take the square root of both pieces. So the 6, so the square root of 36 is 6. That actually gets written outside of the absolute value bars. It's not necessarily wrong if you write it in, but it's going to be positive either way, right? And then cosine of theta. So that would be how those ones get written. Now, again, I wrote it out obnoxiously, writing every single step. You do not have to write out all of those steps. This is Riley's version. Josh's version would have about 2 steps. Just kidding.
You wouldn't even have any steps. You just go straight there.
All right, any questions on those? All right. Then there's going to be a lot of problems, but we still have like 20 minutes left. 11, 13, 19, 23, 25, 29, 31, 33, 35, 37, 39, 47, 49, 69, 71, and 73. Now, what I'm going to tell you is some of these problems that are from the same section, if you understand them, that's fine. Part of the reason for me giving you so many is because these are solving using identities and stuff and like simplifying down. And obviously 98% of the time I'm pulling them out of the book. So it's basically just making sure you've seen them before the quiz or the test and understand how to do them. But you do not have to do all of them if you feel like you've got it under control. Like 69, 71, and 73 are all this square root type. I would say maybe do like one of the easy ones and one of the harder ones. So it's a lot, but you don't actually have to do them all. But those are good problems to look at if you are looking for something to do.
Well, I mean, if you're gonna